Hey Alex.
Hi, Sam. Oh, Sean.
Hi Alex, how are you?
Man, this is crazy, bro.
How's it been doing
Man, to
these
me, like,
days?
it's just overwhelming. My God.
Mm,
I'm doing
okay.
two projects. I'm also doing the math project.
How are you?
Yeah, yeah, yeah. Like from the School of Math, we have like two projects, and man, this is crazy.
No worries. How's it coming
How
along?
do you manage to always be on like? I feel like you you always meet your deadline, man. How do you manage to like? It's just crazy.
Oh mate, like I do work every day pretty much to be
Do
honest.
every day.
It's been a bit of a yeah, pretty much.
Yeah.
I mean, if I have breaks here at the moment, it's like 6 days a week minimum, really. Um, it's final year, innit? It's got to be done.
Yeah.
But we move, we move. Has the write up been going? Oh, it's gone.
Hi,
Hi Sam.
how are you?
Yeah, not too bad. Yourself?
I can't complain. Sorry, I'm a few minutes late.
Thanks.
My meeting overran and then rushed into it.
What happens?
Yeah. Okay, so Sean, I gave you access to the Git lab account. Can you see it?
Yeah, I can see it. Yeah.
Okay. Alex, do you have a Git lab account?
Yes, yeah, I can log on to.
Yeah. Could you let me have your username and I can add you to the repository?
Yeah, is my username is SC16AN. I think that's my username because that's how I log on. Just
Yeah. Okay. Yeah. Let me see whether. Um, members. SC
16
16 or
16
yeah, great.
and,
I've got you.
and
I've got
AN.
you.
Yeah.
Great. Okay, so So what I've done is there's a there's a graph package called there's a Python graph package called NetworkX, which is rather complicated. I think overly complicated. So what I've done is I've taken a similar approach to it, but I've just implemented a simple graph data structure. And I'll share my screen now. Let me just open the file first. Okay, so can you see my screen?
Yeah.
Okay, so so this is the repository that you've now got access to, and there's a package called PyGraph, and inside here there's a single file called graph.py. Well, there's also a thing that makes it into a module, but and the main thing that's inside here that you'll be interested in is the graph object.
Mm-hmm.
Now, we know that a graph consists of a set of vertices and a set of edges.
Yeah.
So what we've got is internally inside the graph structure, there's a dictionary which contains a set of edges. Sorry, that contains a set of vertices, right? And the vertices are used as keys in that dictionary. And the value that's stored against them is itself a dictionary of edges, right? So if I just so if I do something like this, what we've got is now G. Sorry. G is a graph object,
Right.
right? And we can do things like, so I can do G dot add vertex, and you can have anything as vertices, and then you can also attach additional data to them. So you could do something like color equals blue, right? And then when you can then like print the graph. It'll just come up with it just has its object. But then you can do things like G dot vertices, which lists all of the vertices in the graph. So let's just create and if we do G dot vertices again, you'll see now that there's a bunch of vertices in the graph, right?
Mm-hmm.
And then you can, if we wanted to remove a vertex, we can do G dot remove vertex, and we just have to tell it which one we want to remove.
Mm-hmm.
And of course, then G no longer contains the vertex 9. And then we can add edges between them. So perhaps we can do something like G dot add edge, and I don't know, let's say we want to add an edge between vertices 1 and 2, and we also want to give that edge a weight 7. We can do something like that. And then if you do G dot edges, I think it's edges, yeah, you can get all the edges. I need to I'll make those prints nice so that they actually print sensible things.
Mm-hmm.
But so what you can do is you can do things like edges 1. Sorry. So that's the edge that I've just added. It's between vertices 1 and 2, and you can see that the edge weight is set to 7.
Mm-hmm.
So one thing that's worth noting here is that it is set up as a directed graph, right?
Mm-hmm.
So the edge 1, there is an edge between vertex 1 and vertex 2, but there's not an edge between vertex 2 and vertex 1. So if you want the illusion of having an undirected graph, you also have to add
The opposite of it.
Indeed, yeah, just the other way around. And then it works fine. So yeah, so whenever you're modifying the graph, or if you want to modify the graph, you always have to add the pair of edges in.
Right.
Yeah, and I will make some minor changes. So I won't change the interface to this, but I will change a few things so that when it's printing, it's not printing these strange neighborhood views and things.
Mm-hmm.
Because that's a little bit confusing. But what you can do is you can do things like vertices 1, right, and that will bring you back. So vertex 1 has no data associated with it, but if I was to add vertex, I don't know, 10, and say, I don't know, put a key in here, and then, I don't know, some more data. That's not quite right. Maybe that's returning edges. I should be able to get hold of the data again. Oh, in fact, I can. Apparently not, in fact. What is that object? No, I should be able to do that, in fact. Or apparently not. So, yeah, so you can store, so each of your, so you've got this basic graph data structure, and you've got the normal things you'd expect. So you can add vertices, you can add a vertex, you can add a set of vertices, remove vertices, remove a vertex, remove a set of vertices, and whenever you remove a vertex, it will also remove all the edges associated with it. So we know at the moment that this graph has 2 edges in between 1 and 2.
Yeah.
But what we can do is if we remove vertex 1, remove vertex 1, and we go to print it out now, so you'll see that it no longer has the vertex 1, but then also, hopefully, if you go to that, vertices, I want a list, bear with me, how do I get a list out of that? Oh, there we go. Neighbours. You can see that it's now got no neighbours, right? Whereas before, if I could just go and add an edge between 2 and 3, and then call it again, you can see that vertex 2 has a set of neighbours. Well, it has a neighbour, which is this vertex 3 now. So for the most part, you probably just want the graph data structure itself. And the items are iterable, so you can do things like for v in g.vertices. Right, and you can ask whether a vertex is in the graph. So you can say things like using the in operator. So 4 in G, and 4 is a vertex of G. Whereas if I do 99 in G, it comes back with false because the object 99 is not a vertex of the graph.
Okay.
You can also do things like g.order, which gets you the number of vertices in the graph, and g.size, which gets you the number of edges in the graph. Thank you. Are there any other functions that you think you'll need on the graph object?
We can store the Can we store the predecessor?
So you can store the So you can. So when you say the predecessor, you mean so you've got an edge, so you've got a vertex. So you're doing shortest path algorithms, aren't you? Mm-hmm. So you're going to want to store additional data and each of the nodes to say which is the predecessor.
Yeah.
So what I would do is I would use the vertex attributes to do that. So do you know when we add a vertex, we can say what the vertex is, but then you can also do something. I don't know, you can do something like that.
Right.
So pred is then an attribute of that vertex.
Okay.
So then if you ever want to go back, if you want to get that vertex, so we could do something like g.vertices 99. What that should bring back, that should return. So vertices is a vertex for you. So I will just. I need to make a modification about that. Just how do I get a vertex? Okay. Sorry. Yeah. Sorry. I will make a small change to this. But yeah. So any additional data that you want to store about a node, I will store it, or in fact, or of an edge, or of the graph itself. You can just add them as attributes.
All right.
And I think that's probably the best way of doing it. And everything, so vertices can have attributes, edges can have attributes, and graphs can have attributes as well.
Okay.
And you can get and set them. But I'll provide, I'll push a sample file into the repository, which just contains like a list of all the features that you can do.
Okay, yeah.
Just like a bit of an example of things.
Yeah.
Will you need anything else? So I think you can store the predecessor as an attribute, and that's quite an elegant way of doing it. You just have to make sure that you always call it the same attribute throughout the graph.
Mm-hmm.
Alex, do you need anything?
Uh, I can't think of everything right now, but yeah.
I mean, my only question I would have is that we have the graph, and then for like Floyd Walshall, it runs on a matrix. So
Yes.
I'm assuming we'd have to get this graph, and from that graph generate a matrix that we then pass to the algorithm, sort of thing.
Do you want an adjacency matrix?
No, it'd be adjacency matrix. Yeah, an adjacency matrix. Yeah, sorry.
Okay, so so there's two options. Either you can implement it yourself, so just define a function that you pass it a graph and it returns a matrix, or in fact you could write it inside the graph graph object itself, and it could be a method in the object. It's probably reasonably useful. The only downside to it is that so some adjacency matrices are just like 0, 1 matrices to say that these two vertices are adjacent, but I'm guessing in Floyd Warshall's the way that you want to do it is you want the weight of the edge, or the length of the edge, to be to be the entry inside the matrix. So you'll want to rather than using is there an edge here, you'll want to look up the weight attribute of the edge, and place that in the matrix instead. But I can probably implement that for you. That shouldn't take too long. Is there? Okay, so yeah, I can implement that. Let me just make a list of features. So I need to fix the node data stuff. Fix vertex attributes. And we also want an adjacency matrix. Alex, are you doing shortest path algorithms as well?
Yeah.
Yeah. Which ones are you doing? Are you doing have you got completely different ones, or are you?
I'm doing Dijkstraat and Bellman-Ford.
Okay. So Dijkstra's is straightforward. Bellman-Ford allows cycles of non-negative weight, doesn't it?
Yeah.
Yeah.
Okay, so you won't need any. So you don't need an adjacency matrix or anything. But Sean will. Okay. Okay. Okay, so I can get those. I will add those features in, and I'll push an updated version of the library with those fixes, but also with I'll push a test file in, which just contains like a simple some examples of what kind of things you can do with it, and it should run, and then hopefully you'll be able to piece the algorithms together from the bits of samples that I've provided for you. Is that okay?
Yeah, that's fine.
Okay. When are you going to start implementing things? What's your plan?
I think we've got a bit of time over Christmas, so once I've got my intermediate project handed in, I might have a little stab at it, more just to familiarise myself, and then maybe try and do something over Christmas. If not, I'll start doing it when I get back.
Okay. So I will try and get those features added by like early next week.
Okay.
That's right. It shouldn't be too long. I've just got to be able to steal an hour's worth of time to do it. So I'm not. It doesn't sound like I'm going to be holding you up if I don't do it until early next week.
Oh yeah, not at all.
Okay. And Alex, when are you intending on doing things?
Right now I'm still writing. I'm still focusing on the writing side of it. So it's that to be like next year, like June.
Okay, that's not a problem.
Yeah.
Okay, so if I don't get stuff done before next Monday, then I'm not going to be holding you up. I don't want to be holding you up. That's the key thing.
Yeah, no, it's fine.
Okay. How are you enjoying it so far? Finding it back, or?
Yeah, it's been okay. It's been quite interesting learning about them, especially the all pairs ones, and like going into the history and stuff like that. It's been quite interesting.
The Floyd Warshall's algorithm is quite surprising the way that it works, and the fact that it does indeed work.
Yeah, that one's a bit of you have to get your head around it. It takes a bit of time, but yeah, it's quite interesting. I like Johnson's as well. That's an interesting one because it does because that uses Bellman's and Dijkstra's, and it adds like an extra node to reweight all the edges. It's like a
Okay, I haven't seen that one before. What does it allow you to do? Does it allow you to have negative weights?
yeah, it allows you to do all pairs with negative weights by reweighting them, so they have positive weights, but the shortest paths stay the same by using Bellman's, by adding an extra. It's a
Okay,
bit of a weird one.
That's a bit sneaky.
Yeah, and then it uses Dijkstra's at the end to do it. So,
So are you going to implement that one as well? So you're going to do Johnson's?
I'm going to do Bellman's, Dijkstra's, Floyd Shout, and Johnson's.
4? Wow. Okay.
Yeah.
I think it's doable though. I mean,
Yeah, well, because Johnson's I was a bit concerned, but when it was just using Bellman's and Dijkstra's, and you've got all the pseudocode in the books, so I was like,
yeah, by the time you've gone to the effort of actually implementing Bellman's and Dijkstra's, you might as well combine them together and do the last thing, which is Johnson's. Then. So why not? The next thing is that in terms of what you do, I would like to include in the library for future years, so that next year's students can do something and can perhaps use your algorithms. So perhaps each of the algorithms that you implement should become its own class.
uh-huh.
And then that maybe there's just an execute method on them, on the class itself, on the object itself, and then that somehow computes the return. I mean, the return of the two different of a single source shortest path. The return is just a path, right?
Yeah.
Or potentially a tree.
Yeah.
So you'll also need a way of representing that rooted tree.
Okay.
But that's not a problem because you could just create the graph,
Yeah.
right? And
Could you have like a clock for the algorithm itself, essentially?
Yeah.
One of the attributes would be the original graph, and then once you've executed it, one of the attributes would be the predecessor really
yeah,
creates.
so I wouldn't store state inside the object. What I would do is I would just have a function called execute, and that function returns it. The reason being is because the graph objects are mutable. If I create a graph and then pass that graph as an attribute to the shortest path algorithm, I run execute and then store the result inside an attribute of the shortest path algorithm. If I change the graph and then get the shortest path result again, it won't reflect the new graph.
Right. Okay.
So it only makes sense to store a result if the object that you're working on is immutable. That is, it can't be changed, but the graphs can be changed.
Okay.
I could implement an immutable graph if we really wanted to. But, so perhaps it's just easy to have a function, and that function would just maybe it's sensible just to return a rooted tree, another graph object. Or if you're only ever going to return a single path, so if you say execute and I want the shortest path between a specified vertex and another specified vertex, perhaps it just returns a list of edges that it has to traverse.
Okay.
That could work. For things like all pairs shortest path, no, that doesn't return a rooted tree, does it? It could. You have to think about what kind of object you'd return in that situation.
That returns predecessor matrix. That if you go look at one, it will tell you the next one. So I was thinking for that object, it would do. You could just say for both of them, it would be you pass for this graph. What is the shortest path for this source, this end vertex, and then it would give you all the edges like that.
Yeah,
that's either one.
Yeah, that sounds sensible. So you're going to have an algorithm which implements the algorithm. You're going to have a class that implements the algorithm itself, and then you're going to have some type of internal representation of the predecessor matrix, and then perhaps a couple of methods on it which allow the class to interpret this predecessor matrix, because you don't want to, if you're a programmer, you don't want to be handed back a predecessor matrix as the result, do you?
No.
Because what you actually want is you want the path itself, or you want the set of vertices along the path, or you want the edges along the path or something. You don't want to be given back this complicated data structure which you then have to understand how the paths are represented. So think about being friendly to the programmer. What would you want if you ask for a shortest path? what would you want? Do you want a matrix that then you have to interpret yourself, or do you actually just want the path?
The path, yeah.
Probably just the path, right?
Yeah.
So have a think about what would you expect if you were using this. What would you want?
Yeah. Okay. So could we have possibly multiple execute functions in a way where one of them will just have the predecessor graph, and then one of them will be like, okay, all pairs shortest path, but execute on this graph. But I also want the part what you return is this path, this shortest path, sort of thing.
Yeah. So I think perhaps you could have so for the singles pair shortest path, perhaps you really want two functions. One that returns a shortest path tree, right, where you just pass it the route. And perhaps you also then want another function where you pass it a source and a destination, and it just returns the path path between them, and not all pairs.
Right.
Sorry, and not the from source to every destination. So that would be. I mean, thinking about it, if you thinking about how you would want to use this library, you might want all paths from a single source, or you might just want the shortest path between two vertices. So provide those functions, and as soon as you implement Dijkstra's, it's no difference really to be able to return either of those. And then for the all pair shortest path, yeah, have a think about what you want, because you probably want a similar function to say between two specific ones. But if you're going to do that, then you don't really want to run the all pairs algorithm, because it takes longer. So in fact, for that algorithm, you actually probably want to return an object which is capable of getting between any set of pairs without adding additional, without having to do any significant additional computation. But I'm happy if you, when you get to it and you get to designing it, then I'm happy to sit down with you and figure out what the classes should be called, or how the classes should be structured. And in fact, when you come to implement it, it might be better not to think about it in an object-oriented way. Just write a function which implements Dijkstra's, and then once you've got that done, we can think about how that can be represented as an object.
Okay.
So
yeah.
It's just because a lot of the algorithms, or a lot of the pseudocode in the books, is not object-oriented, and it doesn't even bear any resemblance to a nice object-oriented design. So mainly just get the algorithm done first.
Yeah.
And then we can think about what the interfaces for the object should look like.
Okay, yeah, that sounds sensible.
Great. Okay. So I will. So the key thing is, so I'm going to make some changes to that library. So before you start working on it, whenever you do start working on it, just make sure you do a git pull again, because I might have made some changes.
Okay.
And I'm happy for you to push stuff. You will be able to push stuff into that repository. But if you are pushing stuff, can you put it in your own file, in its own file? If you do want to make changes to the graph file, the graph.py file itself,
Just do it on a new branch.
Yeah, please do it on a new branch, and yeah, try not to break stuff.
I try my best.
Yeah. Okay. Good. So I'll be around. I'm always happy to have discussions about how things work. I like programming. I like theory. So yeah. So anything related to it, just let me know.
Okay.
Good. Right. I've got final year project meetings too. I've packed them back to back all day, all afternoon. So so yeah. So I think I'm gonna have to leave you now. But like I said, if you want anything, just message me in Teams. And Teams is probably better. So I know. Sorry, Sean. I did notice that you emailed me.
Yeah.
My inbox has got like thousands of unread messages in.
Okay, so Teams.
My Teams is better, yeah. So just message me on Teams. And same, Alex, just message me on Teams if you want anything.
Okay.
If you want anything. I'm better with my email at the moment.
Okay, no worries, that's fine. Well, thanks for all your help anyways.
No worries.
Thank you very much.
And if I don't speak to you before, have a good Christmas.
Yeah,
Thank you very much.
Cheers, thank you.
Thank you. Bye. Yo. Who the hell is Bolo Johnson, man? What the hell? Is it Ivoire Noir?